Welcome, good people of planet Earth. This is Ace of the Cosmos. What if I told you that the universe's most destructive forces might also be its greatest tools for travel? Picture this. Objects so powerful they devour light itself, yet they might hold the key to humanity's oldest dream, traveling through time. Black holes. These cosmic behemoths are among the most mysterious objects in our universe. Born from the violent death of massive stars, they possess gravity so extreme that they warp the very fabric of reality around them. Nothing that crosses their boundary, the event horizon, can ever escape, their nature's ultimate point of no return. But here's the mind-bending question that drives physicists to the edge of theoretical possibility. Could these dark titans of space actually be the universe's ultimate time machines? Today, we're diving deep into the physics that suggests the answer might be yes. To understand how black holes could manipulate time, we need to grasp one of Einstein's most shocking revelations. General relativity tells us that gravity isn't just a force pulling objects together, it's something far more profound. Gravity is the warping of space-time itself. Massive objects literally bend the fabric of space and time around them, like a bowling ball placed on a stretched rubber sheet. Near a black hole, this warping becomes extreme. Time itself slows down dramatically compared to regions farther away. This is gravitational time dilation, and it's not science fiction, it's verified physics. The closer you get to that event horizon, the more time stretches and distorts. But there's another effect that's equally dramatic: tidal forces. As you approach a black hole, the difference in gravitational pull between your head and feet becomes so extreme that you'd be stretched like spaghetti. Scientists call this spaghettification. Your body would be pulled into a long, thin strand of atoms. It's a violent reminder of just how powerful these objects truly are. Now imagine this scenario. An astronaut ventures close to a black hole's event horizon, carefully maintaining orbit just outside that point of no return. To them, time passes normally. They check their watch, eat a meal, maybe read a book. But back on Earth, something extraordinary is happening. Years are flying by, decades, perhaps even centuries. When our astronaut finally returns home, they might have aged only a few hours, while everyone they knew has long since passed away. They haven't traveled to a different place, they've traveled to the future. This isn't speculation, this is what Einstein's equations predict with mathematical certainty. But what about traveling to the past, or taking shortcuts across the universe? This is where we enter even more speculative territory: wormholes. These theoretical structures are like tunnels through space-time, bridges that could connect distant points in the universe or even different times entirely. Think of space-time as a sheet of paper. Normally, to get from one point to another, you'd have to travel across the surface. But what if you could fold that paper and punch a hole through it? That's essentially what a wormhole would do, creating a shortcut through the very fabric of reality. The problem is keeping one open. According to our current understanding, you'd need something called exotic matter, a substance with negative energy density. We've never observed such matter in nature, and it might not even exist. Without it, any wormhole would collapse instantly, crushing anything inside before it could make the journey. Even if we could create a stable, traversable wormhole, we'd face another challenge: the paradoxes. The most famous is the grandfather paradox. Imagine traveling back in time and preventing your grandparents from ever meeting. If they never met, your parents were never born, which means you were never born. But if you were never born, how did you travel back in time to prevent their meeting in the first place? This logical loop has puzzled physicists for generations. Some propose that the universe might simply prevent any action that creates a paradox. Others suggest that changing the past creates a new parallel timeline, leaving your original universe intact. These ideas push the very boundaries of causality and challenge our understanding of how reality works. So where does modern physics stand on all of this? Today's researchers are pushing deeper into the nature of black holes and space-time than ever before. Observatories like the Event Horizon Telescope have given us our first actual images of black holes, revealing the glowing rings of matter swirling around these cosmic drains. Gravitational wave detectors like LIGO are listening to the ripples in space-time created when black holes collide, giving us new ways to study these extreme objects. Each observation brings us closer to understanding the true nature of space-time and whether it can be manipulated in the ways our theories suggest. The key to unlocking time travel might lie in quantum gravity, a theory that would unite Einstein's general relativity with quantum mechanics. Right now, these two pillars of modern physics don't play well together. General relativity describes the large-scale structure of space-time, while quantum mechanics governs the subatomic realm. At the heart of a black hole, where both theories should apply, they give contradictory answers. A successful theory of quantum gravity might reveal new possibilities for manipulating space-time that we haven't even imagined yet. It could show us whether wormholes can truly exist, whether time travel is possible, or whether the universe has built-in safeguards that prevent such paradoxes from ever occurring. But let's say we did crack the code. Let's say we figured out how to build a time machine using a black hole or a wormhole. Then what? The ethical implications would be staggering. Who gets to decide who travels through time? What happens to free will if the future can influence the past? Could time travel be weaponized? These aren't just philosophical questions. They're practical concerns that would need answers before we ever turned such a device on. Black holes remain among the most enigmatic objects in our universe. They sit at the intersection of the largest scales we can observe and the smallest scales we can theorize about. They challenge our understanding of physics, push our mathematics to its limits, and force us to question the very nature of time and space. Understanding black holes isn't just about building a time machine someday, it's about comprehending the fundamental fabric of reality itself. Every question we answer about these cosmic mysteries brings us closer to understanding how the universe works at its most basic level. We're not just studying objects in space, we're studying the rules that govern existence. The universe is vast beyond comprehension, filled with wonders we're only beginning to glimpse. Black holes might be time machines, or they might not. But the journey to find out is pushing human knowledge forward in ways that will echo through generations. Every observation, every calculation, every theoretical breakthrough brings us closer to unlocking secrets that have been hidden since the dawn of time. So keep looking up at the night sky. Keep asking questions. Keep wondering about the infinite possibilities hidden in the darkness between the stars. The universe is far stranger, far more beautiful, and far more full of potential than we ever imagined. And if you want to keep exploring these cosmic mysteries with me, hit that subscribe button and smash that like button. Let's journey through the universe together, one mind-bending discovery at a time. This is Ace of the Cosmos, reminding you that the greatest adventures aren't just out there in space. They're in the questions we dare to ask and the boundaries we dare to push. Until next time, stay curious.